Thank you. So lots of acknowledgements. I mentioned the Perks project earlier, and acknowledgements on the left-hand side. That's a big project. I'll allude to it in a couple of slides. Involves hardware work, software work. And in IBM, it's a project that includes people from our research division, our software and systems product groups. And on the right-hand side, our acknowledgements specifically related to the X10 language, which I'm going to talk about. A number of people have contributed ideas. It's still very much in the idea formative stage, and implementation has begun. There are only about 3 people working on the implementation, but it's great to have a large community of people where we've been bouncing these ideas, and each one has been calibrating them based on their expertise. So the topic of this talk, we've recognized some benefits of VEs, virtual execution environments. The ABAP talk notwithstanding, they do provide safety, productivity, and so on. The question is, are they ready to play the big league in terms of play with the big machines? So what are the challenges facing future parallel systems? And by future, we're looking out to about the 2010 timeframe, 6 years from now, which kind of makes us think that we have a window of 3 years to really explore new ideas, and then another 3 years of productization. So it is a step beyond being constrained by today's product limitations. And there's some serious challenges when you look that far. There's the memory wall, which you're all familiar with. The data access distances within a chip across chips is increasingly non-uniform, even accesses to different parts of an L2.
So the memory wall is already happening today,
Yes,
right?
yes, and it's getting way more severe with multiple. Yes, it's already happening. These trends are emerging. The second is what I've called the frequency wall. This is the whole issue of SMP on a chip. It's been alluded to since yesterday. And what's happening is there's a slowdown in frequency scaling. That's really happening for thermal power management reasons. So actually, just a little bit of a digression here. We were talking about Probsting's law. And the way I see it, what's happened is the technology people are the one who's provided us the rising tide for the last 20 years. They've just used lithography to reduce the devices, and processor architecture designers tinkered with new ideas on top of that, and compiler people tinkered with new ideas. But if you, I think, normalize with respect to technology, I would say that the compiler contributions probably exceeded the processor architecture contribution.
Right.
So that's, but what's happened is you could continue making the devices smaller, but now due to physics reasons of leakage current and so on, it gets too hot. And if you can afford a water-cooled machine, then fine, you could continue scaling the frequency, but you can't. So frequency is not going to scale. So the hardware is changing in ways that software is going to have to care about. In the past, software couldn't really be bothered, what the semiconductor technology was. And what's happening is there's a trend towards simpler cores in the chip, and in particular, this hierarchy of parallelism, which by 2000, it's already emerging, but by 2010 is going to be very much a reality. So scale-out parallelism, where you have these clusters, but they're tightly integrated, like blade servers. They have a dedicated interconnect. So we're not talking about the grid over there. We're talking about one box with scale-out parallelism. SMP across multiple nodes, across multiple chips, within a chip, multiple cores. So then coprocessors. We've already heard examples about graphics unit. IBM is part of this consortium with Sony and Toshiba for the cell processor. SMTs. Vector SIMD level parallelism, instruction level parallelism, and it's going to be there in the hardware. And much as you can try and ignore it as a software person on ISV, you ignore it at your own peril in that time frame. Because if you just say, okay, I'm just going to write a single thread, increasingly, you're going to underperform with respect to your competition. So that's an issue. And finally, scalability wall. If you really look at the large-scale machines by that time frame, we expect to need of the order of 100,000 threads to keep the machine busy. And even the HPC folks who are used to domain decomposition are balking at that kind of number. They can't just get it by dividing up their data set. So these are serious challenges. And do VEs have a role to play? And then in addition to hardware challenges, there are various software challenges. Productivity, concurrent programming is hard. That's going to be a key topic of what I want to talk about. Reliability challenges, does the VE have anything to offer over there? And business challenges, it can't just be a one-off solution. It should be a system that is useful for multiple domains and provides software that can live for multiple hardware generations. So, tough problems. Well, at a very high level, and I'll go into some details, the answers, are these virtual environments ready? Probably not yet. I mean, you're not going to run your fastest supercomputing application, the fastest supercomputer on a JVM or on the CLR. That's not going to happen today. But there are encouraging signs. And I think what's interesting is the lessons being learned in the commercial domain and the HPC domain, different kinds of lessons which could actually come together. So in the commercial domain, experience has been gained, first of all, how to make programmers more productive. I think this has been much more successful in the commercial domain than the HPC domain. Simplifying programming models, we heard about it from the database folks, the SAP talk, etc. And also a lot of investment in virtualization, isolation, and so on. In the HPC domain, there's been a lot of experience with these distributed memory machine configurations which are tightly connected together with a dedicated interconnect. And one thing that's sort of helped serve as a catalyst over here, certainly provided an organization framework for what we are doing, is this DARPA program in high productivity computing systems. Of which 3 participating vendors in the current phase are Sun, IBM, and Cray. And I don't know all the details of what Sun is doing, but I'm going to assume that their strategy is based on a virtual environment. Certainly IBM's is, and Cray's maybe not, but there's a role to play over here. And finally, this workshop I think is promising. We're hearing about experiences and innovations coming in this whole area of virtual environments. And I think putting these together, I'm pretty optimistic that this technology can serve those challenges of the HPC large-scale parallel machines in the 2010 timeframe. There's a lot of work to be done to get there, but I think we can. Oh, this is just a bureaucratic type slide from DARPA, just to give you the time frame. We are in what's called phase 2 of this program, which runs from mid-2003 to mid-2006, which is very much a phase of technology evaluation and prototypes. So we're not shipping, production systems in this phase. And this is gearing up towards the kind of production systems we built in 2010. So it really does give us an opportunity to step back and look at hardware and software design issues with this longer time horizon. So the PERCS project in this program, just very briefly to provide the context, is one that includes looking at innovations on the PERCS system hardware. It is as a follow-on to the PowerPC roadmap, but looking at that time frame, what could be done. System software in phase 2, we're experimenting with K42, which has been mentioned earlier. Then we have the language runtime. I mean, that's really the virtual execution layer. And also the continuous optimization that Evelyn mentioned earlier today. For programming languages in this evaluation mode, there are a few different languages we're experimenting with, because part of the goal is really to do a comparison to see if the new ideas are worthwhile or not. So we have mature languages, and Java's joined the crowd of mature languages. In fact, there's now legacy code in Java. There are these experimental languages. I'll talk about X10. With our university partners, also we're working on StreamEd, variant of MATLAB. And then on top of these languages, there are programming models, which are sort of the idioms or paradigms on using these languages. And there again, we have this new model exemplified by X10, but we're also going to compare it with OpenMP and MPI. And a substantial investment in tools. I'll say a little more about that. And the focus is really on increasing productivity. The term productivity in this program is used in a very general setting to refer to execution productivity, which we call performance, and also development productivity. Okay, so in the development productivity area, we were given this grand challenge to say, can you improve application development productivity by a factor of 10 by 2010? Now you might start getting some clues as to where the X10 name came from. So we've been looking at this, and this is a